Hi, my name is Nathan, and along with Teen and Kevin, we make up Group 38. For our semester project for neural networks, we decided to make something called FacePALM. And what FacePALM does is it identifies emotions using convolutional neural networks.
Facial emotion detection and emotion analysis has a large number of applications both in theory and in practice. Some of these include, but are not limited to, physical and mental health diagnosis, customer feedback analysis, assistance for those with visual and communicative disorders, and improved video audio description. So for our model, we plan to create a visual-based model to extract human emotion from still images of facial expressions. We plan to incorporate a convolutional neural network that will be trained to find features and patterns in images and label them as a specific emotion accordingly.
For our dataset, we chose the FER 2013 dataset, which is open source from Kaggle. There are 35,000 images total, with about 28,000 being for training and 7,000 being for testing. It has 7 categories of emotions, which include anger, disgust, fear, happiness, sadness, surprise, and neutrality. We chose this dataset because of its community support and its standardized images, which are in 48 by 48 pixels and are black and white. For the inputs outputs, we have a 48 by 48 pixel grayscale images from the dataset, and any new images not from the training or testing dataset would have to be scaled and converted to match that dataset. For the outputs, we had a numeric label from 0 to 6, which corresponds to an emotion, as described previously. For example, 3 would represent happy.
Data augmentation was applied to our dataset in order to increase training data, counter unbalanced classes, and improve model generalization. We applied random rotations, increase and decrease in contrast, brightness and scaling, all in conjunction, and appended it to our dataset. The amount of augmentation was based off of a multiplier, which represented by how much we wanted to increase our data, with the best resulting value increasing our data from 22,000 training images to 130,000. This increase in data came with some complications, most prominently with that of storage size. For our transfer learning approach, which we will get into a bit more detail later, image data needed to be fully loaded. So we had to use a new dataset loading technique to load image files only when needed and discard when done. Using this greatly helped managing runner model training and testing on local devices.
For the baseline model, we used the CNN and we used the Atom optimizer alongside it. For the training and testing data for the model, we had an 80-20 split, and within that training data, we had another split of 80-20 for validation. We ran this for 20 epochs and received a result of 58.12% accuracy. As can be seen in this slide here, the accuracy curve demonstrates that we have some overfitting, and that the learning curve shows that the model was not really being representative of the data.
In an effort to try to improve upon the baseline model that we started with, we tried out a few different models that we tried to make a compressed version of from a popular model. So we took LayNet 5, AlexNet, and VGGNet and tried to make a compressed version that would work with a 48 by 48 pixel image. And unfortunately, we received unexpectedly poor performance. And this was likely due to the lack of data, as these models were 1, larger, and 2, trained on ImageNet, which had 1 million plus images, where we had a fraction of that. So likely we would have needed a whole lot more data, and as well more epochs to be able to properly find the patterns using these compressed custom models. As such, when we went to do our final model, we went and did a different approach, namely transfer learning with pre-trained models. So we used ResNet 34, ResNet 50, and SE ResNet 50, with the performance improving as we went from ResNet 34 to SE ResNet 50. SE ResNet 50 includes squeeze and excitation, and this helps to improve the classification of the different emotions. We first started with the pre-trained dataset, which was ImageNet, which was already baked into the model, and then included our additional training data to get the best performance out of the model. We used a scheduler that had an adaptive learning rate to help to reduce overfitting, replaced the final classification layer that was originally there with one that goes to 7 labels, which would be our 7 emotions, and we used gradual layer unfreezing to be able to tune at each level to improve the model without reducing all of the pre-trained things that I had learned before. With our new model, we were able to drastically improve our performance. So before, when we had 58%, we now have 67.56%. And that translates to the balanced accuracy, precision, F1 score, recall. All of those are about 10 percentage points higher than our baseline model. And if you look at the confusion matrix, you'll see that it is relatively balanced among all of the different emotions. While some are a little bit better, namely happy, disgust, and neutral, those ones also tended to have a bit more data, which is in line with it performing just a little bit better. So what we learned is our data set wasn't as good as we were anticipating, unfortunately, and the 48 by 48 grayscale images didn't provide enough information to train on. While we were able to get good performance because the SE ResNet 50 model had a top 1 accuracy of around 80% on its own, we think that we could have done better if we were able to have a data set that had 224 by 224 full color images like the models were trained on.
These are our references, and thank you so much for listening.